the last lecture packet, and there's like about 6 slides of computing applications galore. And one of them is an application that we can prove using expected value. Okay, so this is 3SAT, or SAT. Okay, so the general 3SAT problem is you're given a logical expression, and just to reorient you as to what these symbols mean, because I know Macam might have been a while, these are ands, okay, little these things, and these V's are ors. Okay? The upside down L's are negation. Okay, so in a 3SAT problem, you're given a conjunction, sort of like this. There's an example of literals that come in a disjunction of 3 literal pairs. Okay, so these are 3 triples, I guess. So we have x1 as an input variable, x3 there's negation, so not x3, or x4. Okay, and the objective is to satisfy all or as many of the expressions as you can. Okay, a 3SAT problem is in a normal form called 3CNF, and 3CNF looks exactly like this. Each clause has 3 literals in it. And there's a theorem that says you can transform any logical expression that you can dream up into 3CNF. Okay. Now, why is this relevant? It turns out that a lot of real-world problems are things that you can express using logic. It might take a little bit of sweat, but you can translate into logic. Often you would ask a computer program to translate that into the corresponding logic, and then you ask the question, is this thing true or not? Can you find an input that will make it true? That's satisfiability. Or it could be that there are a bunch of constraints about the world. You just, one of my colleagues actually used to do NFL scheduling. Some of your NFL fans, they would try and dream up schedules that would satisfy all the constraints for a season of football. Okay, so 17 weeks, 32 teams, or 34 teams, I forget. Anyway, there's a whole bunch of constraints about who to play in which division in what order and this sort of thing, stadiums, and you can list out all the constraints mathematically and then ask a computer program to find as good a solution as you can. So something that will satisfy as many constraints. You can view each of these brackets as a constraint and solve as many of these as you can. Okay, so this is sort of in the world of automated logic, if you will, and there's a lot of work that's done. It's a very relevant problem. Okay, but we're just going to look at a toy example here. All right, and some of you have actually tried to solve this because it's been on the overhead for on the screen for I don't know a few minutes now. And the objective here is to maximize the number of brackets. Okay, so in this expression we have 4 input variables: x1, x2, x3, and x4. And the objective is to try to find inputs that will make as many of these things true as you can. Now, maybe I'll just let you look at it for 30 seconds. There is a solution that will satisfy all of them, actually. See if you can find it. How'd you do? How many of you found a solution that satisfies all of them? How many of you found one that satisfies 3? How many of you didn't do what I asked you to do? Most of you. Excellent. That's great. Thank you for following the leader. No, I really, really wanted you to look at this thing. Okay, well, let's see. Maybe one of you has a solution that satisfies all 4 of them. Do you have one? x1, 2, and 3 are true, and x4 is false? Could be false or true. Oh, interesting. Okay, well, let's see. Let's just try false. Is it as simple as assigning true to everything? Maybe it is. Anyway, okay, so that would give us 1, 0, 1, 0, 1, 1, 0, 1, 1, sorry, 0, and 1, 1, 0. Looks good. Okay, so each of these is satisfied by that truth assignment, and there's probably many. Okay, maybe you found a different one. I guess, this x4 could have been 1 as well, so all true might have worked. Okay, so solution x1, x2, x3 is 1, and x4 is 0, satisfies all clauses. Okay, and if you get all of them, it must be optimal, if we're trying to satisfy as many of them and we got the max possible. But there are some that really fail quite spectacularly, like if you did x1, x2 is 0, x3 is 1, and x4 is 0. Okay, then the first one's not satisfied, the second one is, the third one is, and the fourth one is not. Okay, so you only get 2. Okay, so it satisfies only 2. Okay, so you understand what the problem is, right? Okay, so you're given an input with a whole bunch of different variables and a whole bunch of different clauses, and you're asked, is there a satisfying truth assignment for this? Okay, so this is called SAT, and if you're trying to maximize the number of clauses, it's max 3SAT. Okay, so we'll put this discussion on hold for just a second. We're going to solve this, but we need to talk a bit about something else in the computer science world that many of you have heard of, because you're computer science majors, right? And it's P versus NP. And this is one of the most famous theoretical computer science problems out there that's unsolved. Okay, it's open. And it's even made its way into the mainstream media. I watched an episode of Numbers back when Numbers was sort of a thing. That's about a cop and a mathematician who are brothers. And whenever the mathematician sort of got upset, he would go into the garage and try to prove P equals NP. And he wouldn't get very far because it's the hardest, open problem out there. So, people would have to come in and have an intervention and talk him down. So this is sort of the, anyway, it has made its way into pop culture. And here's what P and NP mean. Okay, so you as computer scientists should know what these two things mean. Okay, so P is the set of all all problems that can be solved by a polynomial time algorithm. Okay, P polynomial. Okay, so formally, if you have a problem in P, where you have a solution algorithm A, and remember how we measure running time as a function of the size of the input. So any input of size X has, or we say, sorry, of size N, you can say N to the K. Okay, so it's big O of N to the K in general. Now, these are called efficient algorithms. Theoreticians break it down as tractable and intractable by it's in P or it's not in P. Okay, and yes, there are some problems that are provably not in P. They cost exponential time. Okay, so now I don't know that this notion of efficient is good because n to the 100 is not a good running time. You probably haven't seen an n to the 100 algorithm. I haven't. I think the worst I've ever seen was n cubed log n. N cubed is not a great running time either. All right, and some I don't know, real algorithms. I think I've seen the worst one is about n to the 6th. Beyond which it sort of becomes as bad as exponential. But anyway, this is the definition that they go with P. Okay, so polynomial time running time. The set NP is similar. It's the P and the NP means polynomial, but the N stands for non-deterministic. Okay, so non-deterministic is a word that we have sort of seen elsewhere in this course. Now, where have we seen non-deterministic before? Non-determinism means that the execution path of your algorithm is not necessarily known ahead of time. It's not determined by the algorithm itself. And where have we seen that before? We toss a coin in the middle of an algorithm, right? We randomize our algorithms. So we toss a coin, we go left, we go right, we pick a random pivot. Okay? So the execution path is dependent on a bunch of coin tosses. That's what non-determinism has meant to us. In this case, non-determinism means that you can make a copy of yourself. Okay, so your execution parallelizes itself once per unit time, usually say once a second. Okay, and you can sort of you can try true this way or false this way, basically. And then after another second, each of those can try true or false in another way. So they branch and branch and branch in some sort of exponential way. But if the result is no, then we discount it. Okay. So if any of the execution paths say yes, any one of them, the answer is yes. Okay. Otherwise, the answer is no. Which sounds familiar. It sounds like it's a Monte Carlo algorithm, right? Because you toss a coin like you do a primality test or whatever, and it says no. Okay, so you try again, and it says no. Then you try again, it says no. And try again, it's a composite, It said no. And after enough tries, you start to believe that it's actually prime, right? Okay, so very similar to this, except it's going to try every single thing in parallel. This is basically what the non-determinism here is. Okay, so if you compare the two things, the randomized execution path is actually like one path that goes down by taking coin tosses, and NP is like taking every single possible set of coin tosses, all at the same time. It's arbitrary, yeah, so it's per unit time. So I just say once per second per unit time, but you can't do like, you can't fission yourself n times at once. So it's only one way or another way. So it's only a binary decision, yeah. We check the result at the end of each second. It's sort of like, no, not exactly. All the copies of yourself sort of live in parallel universes, sort of like everything everywhere all at once, right? And they all sort of come together. They're all exploring things in parallel. And if any one of them says yes, then the sort of the God process who spawned them all knows that it's a yes. But only if all of them say no is it a no. Yeah, when do we know? If any of them turn up yes, then it just sort of truncates all the other ones. They're all in parallel. So you can imagine there's like infinite or unbounded amount of communication between them. Yeah. Right, so the algorithm is finite, all right? So just to be clear here about the polynomial time, it is a finite amount of time. So when all execution paths have terminated and everybody says no, then the result is no. So it's not an infinite computation, right? But it's once you're done fissioning and trying all possible things, possibly in parallel, it's bounded above by this polynomial time. Good questions, guys. Anything else? Okay, so why am I mentioning this? Because satisfiability was the first problem in NP that was known to be hardest. Okay, so this is known as being NP complete. The complete suffix means that it's the hardest problem in any one of these sets. Okay, so what does hardest mean? It means that if you had this problem available to you, you could solve every other problem in the set with only a little bit of extra time, like maybe polynomial more time. The guy who proved that satisfiability was NP-complete, this was the first problem that was known to be NP-complete, is one of Canada's most famous computer scientists, Stephen Cook. And on the previous slide, that was the young Stephen Cook. And and he was when he first proved it back in around 1970. And this is the mature Stephen Cook today. Anyway, NP completeness, SAT is the hardest problem. Okay, so SAT is known to be very difficult. Everything that's polynomial time computable is certainly NP computable, and it's largely believed that not everything in NP is NP. Okay, even though this is the open question: is P equal to NP? Problems like 3-SAT or SAT don't have polynomial time algorithms. No one has found one yet. If anyone found one, then because it's the hardest problem, everything in NP would be solvable in polynomial time. Okay? But no one's found a solution yet. Anyway, once Cook had this problem, he was able to prove some other natural-sounding problems were also NP complete by saying that they're also the hardest problem. They can actually solve SAT if you treat them right, if you give them the right input. And here are a few other examples. Subset sum is a very natural-sounding problem. If you have a list of n integers, can you find a subset of them that sums to the target t? Sounds easy enough, but if you think of any brute force algorithm, you would have to take 2 to the n possible subsets, right, of A. Okay, so that would be like the most obvious thing to do, but that's a 2 to the n, order 2 to the n algorithm. Traveling salesman is a sort of a graph searching, a routing problem where you're in a network, and the plot is that a salesman needs to go among n cities, and there's a certain cost to traveling between those cities. What's the optimal way that they can go, or can they get there with at most k cost, time or money or whatever it is. And then there's graph algorithms. You've heard of four-coloring, right? You know four-coloring? Okay, well, some of you know four-coloring. Anyway, there's a four-color theorem that says any planar map can be colored with at most 4 colors. Okay, so that means each adjacent region doesn't share the same color, so the map is readable. 3-coloring is just for general graphs, so if you had a graph, is it 3-colorable? So in other words, you give a color to each vertex, and no vertices that are adjacent can share the same color. Okay? All of these problems turn out to be probably hard, okay? But they're equivalently hard. They're all NP complete, and there are many, many others that are really cool problems as well. And if you want to get famous in a hurry, all you have to do is solve one of these things. Find a polynomial time algorithm. I tried at one time. I spent a few days on it, and I wasn't too successful. So it's fun, and the problems look deceptively simple, but they're really hard. Okay, what are we doing today? We are going to use randomization to have an approximation algorithm. This is a common method for dealing with NP-complete problems, is to find an algorithm that gives you something that is close to optimal within some factor. And we're going to do that using randomization. First question we have to deal with, though, is we need to ask the question, is max 3-SAT NP-complete? It should be, okay? If you used it, if you think about using it as a subroutine, you could use it as a subroutine to solve SAT, right? You just pump in whatever you passed into SAT, you pass it into max 3-SAT, and you look at the answer. And if the answer equals the number of clauses, then it's satisfiable. And if not, then it's not. Okay, so we suspect yes, because you could use it to solve 3-SAT. Take any input to 3-SAT, and that is some expression phi, and you pass it to max 3-SAT, and the output is some number opt, and if opt equals k, then phi is satisfiable. And I guess it's an if and only if relationship. If not, then it's not. Okay, so if the best we can do is to satisfy everything, then we're good. Okay, so we're not going to solve SAT today. I swear it, I promise. But we are going to show Johnson's algorithm, okay, which is a randomized algorithm for trying to satisfy as many clauses as possible. And what is Johnson's algorithm? Johnson's algorithm is try a random assignment of true-false to all the literals. Okay, so there are k literals, flip k coins, or I guess n coins. I have n literals and k clauses. That's what I got backwards. Okay, so you do a random assignment, and you're going to get, on average, 7/8 of the clauses are going to be satisfied. Okay, well that sort of makes sense, right? Each clause has 3 things in it, and 3 literals in it, and it's 50-50 whether it's going to be good or not, right? For each of them, independent of each other. Okay, so yeah, the only way that it comes out bad for you is if all 3 of them are false, right? So 1/8 of the time. So 7/8 of the time, it will be satisfied. Okay, so we do our usual trick. Okay, so we're going to write out an indicator variable that it's satisfied, and the expectation of this equals the chance that it's satisfied, which is 1 minus the probability it's not satisfied, which means all of them have to be false, and they are false with probability 1/2 independent of the others, so they multiply. So 1 minus 1/8 is 7/8, and this applies to each clause. Okay, so if Z is the total number of clauses that are satisfied, then the expectation of Z will look like this, but we can use linearity to move the expectation inwards like that. And expectation of each of these is 7/8, so adding a constant to itself, k times, gives us 7/8. Yeah. And so toss a bunch of coins and you'll get, on average, 7/8 of the clauses will be satisfied. Now, Johnson's algorithm is a lot like the other algorithms that we've seen, where we toss coins and hope for the best. It might not come up as 7/8, right? Johnson's algorithm makes a claim that if you try long enough, and you don't have to try very long, but if you try long enough, you will eventually get a truth assignment that's at least as good as 7/8 k. What sort of reasoning do they use? Well, first let's talk about the probabilistic method, yeah? Hey, the probabilistic method is a proof technique where it's sort of a proof of concept. It's sort of like how the pigeonhole principle works out sometimes, right? In the pigeonhole principle, you sort of count the number of things, and you make some counting argument, you count the number of other things, it's pigeons and poles, and by the pigeonhole principle, there are 2 pigeons that have this property, and there's no recipe that tells you how to find them, right? That would, if you had a recipe to find them, that would be a constructive proof, okay? So it would actually list out a recipe, right, like an algorithm, of finding the 2 things that have the matching property. Okay, that's a constructive proof. An existence proof that is non-constructive doesn't give you a recipe. Okay, so it's just a proof that this thing must exist. Okay, so this is another sort of thing like the pigeonhole principle, but in the probabilistic method, the thing that you're claiming, the only thing that you prove is that the probability of a property is less than 1, or a probability of not a property is less than 1, or a probability of a property is greater than 0. It's something other than 100% or 0%. And if such a thing, if you can prove such a thing, then there must exist something that has that property. Okay, so that's the existence. It doesn't tell you how to find it. It just says, it must be there. Okay, so as an application of this, I just want to use it here and say, for any instance, if you look hard enough, okay, so the probability of finding a truth assignment that has at least 7/8 of the clauses satisfied is non-zero. Now, why is that? Well, the average is 7/8, and you have to hit your average sometime, right? If everything was less than the average, then does that even make sense? Is everyone a below average driver? No, it can't be the case, right? We're all above average drivers, right? Yeah. So you can't have everything below the expectation. Okay, so proof, a random variable must sometimes achieve its expectation. Now, just because that's the case doesn't mean that it's going to happen a lot. There are distributions, as we saw last time we were talking about Markov, where all the stuff could just be epsilon before 7/8. All the distribution, pretty much, except for just a little hair, is above 7/8, and it might be very hard to find that sliver that's above 7/8. Okay, so just because this is true doesn't mean there are a lot of cases where it's true. Okay, so this is just an existence proof, as it is right now. It turns out there's enough of cases that are above 7/8 that it doesn't take very long to find a solution that satisfies at least 7/8. And that's what Johnson's algorithm is. Okay, it is just keep trying, keep tossing coins until you find an assignment that works. And his claim is that a random assignment satisfies at least 7/8 of the clauses with probability 1/8k. Okay, this is not 1/8 k. This is 1/8k. K is in the denominator. Okay, and if this claim is true, we're going to prove it next. Then it satisfies a geometric distribution, right? So this would be GO of 1/8k, which means the expectation is 1/8k is 8k. Okay, so you should only have to toss coins at expectation 8k times, and you'll trip over a solution that satisfies 7/8k. Okay, proof. Okay, so the rationale here is to use integer rounding, and I'll show you what the key step is. It's not a very difficult thing. but we use integer rounding to make sure that the separation between these distributions, we can't just have the bulk of the distribution just sitting epsilon below 7/8. Okay. Okay, let's define a quantity. P sub j is the probability exactly j clauses are satisfied. And let P be the probability at least 7/8 of the clauses are satisfied. Okay, P is the thing that we're trying to solve for, because that's the probability at least 7/8, that's the thing that we want. Okay, and we're going to use the expectation formula. Okay, so the expected number of clauses that are satisfied follows whatever the distribution of number of things satisfied are. Okay, so we'll go from 0 all the way up to k clauses. Okay, the number of clauses that are satisfied is j times the probability that j clauses are satisfied. Okay, this is the definition of expectation. And we're going to break it up into two individual sums. One is the number of clauses are less than the target that we want. Okay, so j is strictly less than 7/8 k. And the other is that it's at least 7/8 k. And I'll give you a moment to catch up. Okay, the key step. Okay, so if we look at this value here, okay, j is going to be at most whatever the max of this thing is, and it can be some integer value that is strictly less than 7/8 k. And due to integer rounding, the most it could possibly ever be would be 7/8 k minus an eighth. Okay, because we're dividing by 8 here. Okay, so this thing. Okay, so this thing we're going to approximate by that quantity. Okay, which is just by integer rounding, just 1/8 below. Okay, and that is a significant enough slice. Okay, so that j is this is the most it could ever be. Okay, so we're going to pull it out as a common factor. And I'll rewrite the rest of it. Okay, so it's not j cannot be 7/8 k minus epsilon, where epsilon is some arbitrary real number. It's got to be something in eighths because we're dividing by 8, and the way that integer division works. Okay, the rest of it it's not much to do. Okay, this here I don't know what the probabilities are, but they're definitely less than or equal to 1 in total. That's a pretty gross approximation. Pj is a probability exactly j clauses are satisfied. J is at least the number that we want. This is less than or equal to p. That's the thing that we want. This bit here is also j is less than or equal to k, I guess. Okay, so you put this all together, and this is less than or equal to 7/8 k minus an eighth times 1 plus k times p. And I would put brackets around it, but I ran out of space. Sorry. Where does the 1/8 come from? Okay, so if you think about how, so j has got to be less than 7 divided by 8 times k, which, it might be an integer or it might not be an integer, but if it is an integer, the closest you could, so 7/8 k could be, it could have a remainder, it might not, if you divide by 8, right? So, it could be that j is an integer that's, the integer part of that, or it could be that it's, just 1/8 below in the case where it is an integer. So the most convincing thing we can say, because we're dividing by 8 here, is that it's at most 1/8 below. That's it. Yeah. Okay, well, this is 7/8 k. And if you look at what's happening on the right-hand side, this and this will cancel. So you can toss, let's see, you can toss this minus an eighth over here, I guess. And you'd end up getting pk is greater than or equal to an eighth, or p is greater than or equal to 1/8 over k. Good? Was it worth? I don't know. I saw empty completeness when I was an undergrad many years ago, and I thought it was like one of the coolest things ever. I'm a little surprised at SFU's curriculum that they actually don't require you to be exposed to this concept, because there's a lot of problems in industry that people will ask you to solve, and they're really stinking hard, and it's important for you to have this in the back of your head and go, is this one of those really stinking hard problems? At the very least. Have you seen people's NP or NP completeness, that sort of thing before? A few of you? Just a few of you? Did you have a question? No? Okay, sorry. Sorry, honestly, I've never tried this algorithm. I mean, this is a pretty coarse approximation of what's going on here. I suspect it will converge faster than this. That would be my guess. But yeah, this is just to show that it's tractable. You only have to do it when you're out of work. Yeah. Where do the approximations of the sums of pj come from? I mean, they are very gross, right? The sum of all these probabilities is certainly less than 1. I mean, that's pretty gross, right? But, because the sum of all the probabilities has got to always be less than or equal to 1, right? They are mutually exclusive, yeah. So, because it's the probability exactly j clauses are satisfied. So they partition the set, right? The pj's partition the set. Here, this is less than or equal to, this is less than or equal to p, because of the way we define this, the probability is at least 7/8 k. Yeah, so the pj's are going to be different, probably. It's not a sum of constants. Yeah, p is a constant for whatever formula you have, but that's what we're trying to bound. I don't know if that's clear or not. Okay, we've got 10 minutes to do a little bit more Markov, so let's just do a little bit more Markov. So let me just refresh what we did last time. So I brought this example that says, the average of IQ is 100, it's at least a non-negative number. And we used the fact that it was non-negative to bound the probability of someone having an IQ of 300 or more. I know that seems a little ridiculous. Nobody has an IQ of 300 or more, but just by knowing the average and the fact that it's non-negative, we sort of have this, I use the seesaw example, but for everything that's in the below average case, it has to counterbalance something that's in the above average case. And what's the worst we can do, or best we can do? We can have everybody at 0, except for some people who are 300. And so we know that the ratio is going to be 2 to 1. Okay, so at most 1/3 of the population has a intelligence of 300 or more. Okay, this sort of technique is known as Markov's inequality, and we proved it last time. Basically, if you you want to know how probable is it to be C means away from the mean, or something like that. Not means away from the mean, but means above the mean. Anyway, the probability is 1 over C. Okay, or you can pick any arbitrary x and you divide the mean by x. Okay, so let's look at a couple of examples of this. Okay, so running time of algorithms. Okay, so if you know the average running time of your algorithm, okay, so some sort of probability distribution that's been computed is n. Because running times, let's just write that down. Okay, so running times are non-negative, right? So Markov's inequality applies. Okay, so what is the probability that the time it takes to run is 2n, if the average is n? Okay, well, it's the average is n, so it's n divided by 2n. This would be a half. Okay, so the chances by Markov's inequality is a half, or a tenth. It's the bound above by 10 times the average, or 100 times the average would be 1%. What about a binomial? A binomial, what's the probability that the number of heads that you toss is 3/4 of the number of coins that you toss? Okay, let's try Markov's inequality. Okay, so the probability that z is greater than or equal to 3/4 n is bounded above by the average. What's the average? N over 2. And we divide by this 3/4 n. And a half divided by 3/4 is 2/3. So the probability that the number of things that you toss, the number of times you get heads is at least 3/4 is 2/3. That's terrible. That's a terrible result. Okay, this is certainly true. But a horrible bound. Why? Why is this horrible? Why is it obvious to you that it should be like 2/3? Like, it's kind of weird, right? 2/3. Why is it bad? Yeah, it should be a lot less than a half, right? Right? Because like the distribution is symmetric, right? We're here. Half of the distribution is over here. Okay, we're asking ourselves what's the probability that it's bigger than this quarter that's sitting over here, and like duh, like this has got to be strictly less than a half. Like we could just bound it by a half with symmetry, and yeah, so Markov isn't very effective here. And we get something trivial by symmetry. The probability that z is greater than 1/2 n is less than or equal to a half already. Okay, which is way stronger. Okay, let's do these two real quick. And I'll do them orally so that we save a little bit of writing. We're running low on time. Okay, n men check their hats. And then each hat is distributed to a man uniformly at random. Okay, what's the probability that the number of hats that are back to their original owners are randomly on n heads? Okay, you think about this problem, like the average number of hats that are going to end up on someone's head is 1. Okay, we can do this by indicator variables easily enough. Okay, so if somebody distributes the hats, the chance that you get your own hat back is 1/n. You add all those things up, n of them, you get 1. So the average is 1. So by Markov, it's 1/n. That's the probability. But the actual probability of getting n is 1/n factorial. Okay, so it's 1/n versus 1/n factorial. Okay, it's not like a great bound. Okay, but if you modify the problem just a little bit, and you had a lazy Susan, these things you get at if you go for dim sum with a lot of people, right? There's a wheel in the middle of the table, and you spin the wheel to get the food, right? So imagine that n people are sitting around this table, and each one of them has a different dish in front of them, and then they spin the wheel. Okay, and it lands. Okay, and you look down, and if it's the same appetizer that you started with, then you win. Okay, so what's the probability using Markov? It's very similar to the hats, right? Except there's only one configuration out of n that's good for you, right? So the chances of you winning, of everyone getting the appetizer they started with, is now 1/n. And the average number of appetizers that you get is actually 1. So Markov is actually agrees. Okay, so it actually is spot on in this case. It's 1/n. And if you think about what's going on here, the number of the distribution of appetizers that you get here, it's 0 everywhere, except for the case where the appetizers all land in front of the people. Okay, so it's 0 everywhere, which is exactly that sort of weird case where we talked about where Markov is that the extreme thing where Markov's theorem comes from. Okay, so this one is really not tight, but this one is. Okay, because of the zeros all being clumped together. Okay, so I'll write a couple words about this for next time. But we'll pick up Markov's and we'll get Chebyshev on.